Assalamu alaikum. Welcome to lecture number 25 of Digital Signal Processing. In this lecture, we are going to learn how to calculate the impulse response with the help of difference equation and the various natures of impulse response obtained from the difference equation. Then we will discuss about infinite impulse response and finite impulse response filters and their pros and cons, and our preference to select any filter. After that, we will discuss the significance of impulse response in determining the characteristics of any system. Now here is another example of finding the impulse response of any discrete time system with the help of its difference equation. You can notice that in the difference equation we have the feedback associated with this equation, which means that this filter is a infinite impulse response filter, and we can also say that this system is having some feedback. You can also notice that we have negative sign with the coefficient, so it will affect obviously the impulse response of the system. By looking at the equation, we can say that this is an infinite impulse response system, but we can exactly determine the impulse response of that system, and we can look at that impulse response to prove that this is infinite impulse response system. So the same strategy will be applied to determine the impulse response of this system as applied in the previous lectures. We first transform our equation into the impulse and impulse response. The impulse is considered as an input, so x of n is replaced by delta of n, and y of n and delayed version of y of n, which is the output, is replaced by the impulse response. So here y of n is replaced by h of n, and x of n, which is input, is replaced by delta of n, which is the impulse function. And we know that whenever we apply any impulse at the input, the output will be impulse response. So the same concept is applied to transform the standard difference equation of the discrete time system into impulse and impulse response, and now we are putting different values of n and determining the impulse response at that particular instant. So first of all, at n is equal to -2, we replace the n in entire equation by -2, and after simplifying the equation, our equation becomes like this, and we know that delta at -2 does not exist, and impulse response at -3 obviously do not exist, so both are 0, and finally we get the impulse response at n is equal to -2 is equal to 0. Now we are changing from n -2 to -1 in the next step. So when n is replaced by -1, equation becomes like this, and in the equation you can see that delta of -1, which we know that it is equal to 0, and impulse response at n is equal to -2, which is again 0, so the entire impulse response at h is equal to -1 will be 0. Proceeding with other values of n, which is n is equal to 0, and you can see that when we put n is equal to 0 in the equation, then delta of 0 becomes 1, because we know that impulse is the function which exists for n is equal to 0 and its value is 1. So by putting the value of delta 0 equals to 1, we get the impulse response at n is equal to 0 is equal to 1. Now proceeding with the other values of n, for n is equal to 1, in n is equal to 1 we have placed n is equal to 1 in this equation, and after simplifying the equation, our equation becomes like this, and we know that delta at n is equal to 1 is 0, so we placed 0 here, and the impulse response at n is equal to 0, so we have to refer back to the previous answer, which is 1, so 0.9 multiplied by 1, and again there is a negative sign with it, so the overall answer will be negative of 0.9. So impulse response at n is equal to 1 will be 0.9. Now again varying for n is equal to 2. For n is equal to 2, our equation becomes like this. The first function becomes 0 for other values of n. For n is equal to 2, 3, 4 and onward. But the impulse response is basically that which we obtained in the previous step, which is this point minus 0.9. So h at n is equal to 1, which is the answer obtained in the previous step, which is minus of 0.9. So we placed minus 0.9 here, and minus 0.9 is the actual coefficient, so after multiplying we get positive of 0.81. Now we further vary n is equal to 3, so we get you can see we have to put the impulse response we obtained in the previous step, which is at n is equal to 2, impulse response at n is equal to 2, this one, and we obtained 0.81, and when 0.81 will multiply with 0.9, and you can notice that here is a negative sign, so the overall answer will become negative. And from this procedure or these steps, you can easily understand that this impulse response is never ending. However, it is converging in nature, but as it depends upon the previous impulse response, and we obtained some magnitude in the previous step, so there will be some magnitude obtained in the current step. So by this way we can conclude that this is the infinite impulse response, which we can also prove it earlier by looking at the difference equation. So when we vary n is equal to 4, 5, 6, so we obtained some values. However, these values are near to 1, but it is not equal to 0. So this response is basically infinite impulse response, but converging in nature, as this response is converging to 0 value. At some point we can say that it will nearly becomes equal to 0. So that's why we are calling this response as a converging response. But you can notice that the impulse response is this, and the generic representation of this impulse response is this. We can represent it in the generic form also. So we can expand this function to obtain these samples values or this sequence. One interesting thing we can notice from this sequence is one value is positive and the next value is negative, and again the other next value is positive and the other value is negative. So this is the alternate conversion between the positive and negative, and when we are going to plot this type of signal, which is obviously a signal because it is a response, and response is basically a signal. So when we are going to plot this type of signal, we get values in the positive y-axis and as well as negative y-axis. However, this trend is converging in nature, but we can say that the values are both sided, or we can say we are obtaining the double-sided converging response. In this slide, I have put a question for you people to determine the impulse response of this particular system represented by this difference equation, and you can notice that I have not put a very complicated equation. Equation is quite simple and similar to the equations we have already solved. So numerical is very much easy, but results are very much interesting. As you can see that in the equation we have x of n is treated as input and y of n is treated as output, and there is delayed version of y of n. So this means that this system is depending upon the previous value of output, or in other words we can say that this system is having some feedback. So this type of systems are obviously infinite impulse response system. So we can easily tell the nature of the system before actually solving or before actually performing the entire calculations, that this system is infinite impulse response system. But when you solve this numerical, you will get interesting results in a way that you will achieve magnitude or the impulse response which is going to increase with respect to the time, because I have put the coefficient in such a manner. You can notice that coefficient is here 1.1. So due to this specific nature of equation, we will get the impulse response which is increasing with respect to the time. So we can say that if we consider an infinite impulse response system, then we can achieve or we can obtain infinite impulse response which can be diverging in nature, or by the term diverging I mean to say that the response is increasing with respect to the time. In the previous cases, as you all know, the numericals we have solved earlier, we are getting the response which is converging in nature, that is approaching to zero value. However, the response was infinite impulse response, but that were converging in nature. But in this numerical, you will notice that your response is increasing with respect to the time. So in this way, we can say that infinite impulse response system can have converging response or can have diverging response. So this is the one criteria or one classification of infinite impulse response system. This you will see when you solve this equation or when you will calculate the impulse response with the help of this difference equation. Now I would like to add another interesting point here. After solving this particular example, just change the sign from positive to negative so that coefficient will become negative of 1.1. Just simply replace positive with negative and the entire equation remains the same. So by just changing the sign of the coefficient and again apply the same procedure to determine the impulse response, and when you achieve the result, you will notice that your response is diverging in nature as well as it is double-sided. By the term double-sided, it is very much clear that the magnitude lies in positive x-axis as well as negative x-axis. So in infinite impulse response, systems or IIR filters, we can have infinite impulse response plus diverging or converging response, and another classification is that response can be single-sided or can be double-sided depending upon the nature of system, which you will see when you just replace the positive sign with the negative sign. So in these two examples, you will achieve the diverging response in both cases, but first response, when you consider the positive sign, will be single-sided response, and when you replace it with the negative sign, then you will achieve double-sided response. So we can say that we have 4 to 5 categories of responses which we can obtain from any infinite impulse response filter. First one is converging response or diverging response, or the subset of converging and diverging response can be single-sided converging or double-sided converging, as well as same is true for diverging response. It may be a double-sided response which is diverging in nature, or it may be a single-sided response which is diverging in nature. So again, all these responses are obtained with the help of infinite impulse response filter. Another response we can obtain, and that is very special case, which is the marginally stable response. This concept you can recall, we already discussed the same concept when we were discussing the classification of discrete time systems. There we discussed about the response of the system, and on the basis of responses we actually concluded that this system is a stable system or this system is unstable system. So response is basically a signal. So on the basis of that signal, which type of signal or which type of response we are obtaining, so on the basis of that response we actually conclude that our system is stable or not. If we are obtaining the converging output, then we concluded that our system is a stable system. But if we are obtaining the diverging output, then we say that we have unstable system. Apart from stable and unstable system, there is also a category which is called marginally stable system. And obviously those systems can be represented by a difference equation, and I am giving you a hint. If you want to try and solve that equation, you are free to solve that equation as well. If you just replace this 1.1 with 1, simple 1 factor or 1 coefficient, then you will obtain the response which is neither decreasing with time neither increasing with time, and that response is known as marginally stable response, which remains constant for all values of time. So that is another special case of system which is marginally stable. Coming back to our discussion of infinite impulse response filters, you can understand, or we can conclude our discussion with these block diagram. Suppose you have IIR filter and you are applying any input to this IIR filter, and with respect to this input you are obtaining the bounded output or converging output. And as this filter is IIR filter, so the response is infinite in time. So we can have bounded or converging output from infinite impulse response filter. But also there is another case in which the same filter is used, but the response of the filter to any certain input is unbounded or diverging in nature. So these two are the possibilities of IIR system. IIR system can produce bounded output or IIR filter can produce unbounded output. But the first case is referred to the stable system. If the filter is producing this type of output, then we term this filter or this system as a stable system. And if the system is producing unbounded or diverging output, we can say that this filter is unstable in nature. But what about FIR system, which is finite impulse response system? So finite impulse response are always stable because they do not involve any feedback. So these type of system are always stable system. But IIR filters, as they depend upon the previous output, they can be stable or they can be unstable. So this is the disadvantage of IIR system, that it can be unstable. But again, irrespective of this disadvantage, we usually prefer to design our filter which is IIR in nature. But we always prefer the first case of IIR filter. We are interested to design such type of filter which is IIR in nature and which can produce bounded or converging output. So we are more interested in the first case, which is the stable case of IIR system. And why we are not preferring FIR system? Although FIR system always produces the stable output, but FIR systems are very complicated to design. And another thing, FIR systems have large number of computation involved with them. So the number of computation also increases in FIR filters, and also the designing of FIR filters are very complicated. So due to these reasons, we always prefer to design our system with the help of IIR filter and the stable case of IIR filters. So we will get the bounded or converging output. So first case, this one is preferable. We design the system with the help of, or we opt that strategy that will produce bounded or converging output with the help of IIR filters. But FIR filters are not preferred as their designing is also very complicated and the number of computation is also increases in FIR filters. So I hope that the concept is clear to you people. FIR system, okay, fine, stable, but number of computation is larger in FIR filters and designing is also very complicated. So we prefer the first case of IIR filter, which is bounded or stable output in IIR filter. In this slide, we are going to learn the significance of impulse response. Although we have learned how to calculate the impulse response with the help of difference equation for discrete time system. So in this slide, we will learn what the importance of impulse response is actually and how we can relate the frequency response to the impulse response. As we all know, the unit impulse function is ultimate time limited signal. that exist for only n is equal to 0 and 0 elsewhere. So if we apply unit impulse signal to the input of system, its excitation will be confined for n is equal to 0. This means we are applying input at time n is equal to 0, so the output will obviously be confined for that particular time, which is n is equal to 0. So if any output signal observed after n is equal to 0, that actually represent the characteristic of this system itself, since the input signal has decayed. For this reason, the impulse response is often called as natural response of the system, because it depends upon the nature of the system. So in this way, impulse response is actually the correct actually tell us the characteristics of the system, because impulse response is the output for impulse. In this way, impulse response is actually telling us regarding the behavior or natural response of the system, because whatever the output we are getting after time n is equal to 0, that is purely because of the system characteristic, because input is only applied at n is equal to 0. So ideally output will also be obtained for n is equal to 0. But if we obtaining the output for other values of n, such as at n is equal to 1, 2, 3 and so on, so that output is specifically due to the nature of the system or characteristics of the system. So that's why this impulse response is often known as the natural response of the system, because it is depending upon the nature of the system. And if we speak more technically, then response actually depends upon the coefficients of the system. Coefficient means the mathematical expression or the mathematical relation to which the different components for which the system is composed of are interlinked, and its mathematical expression and the coefficient appearing in that expression. So response depends upon the coefficients of the system, and usually the range of coefficient for any system is from -1 to +1. So this is basically the one of the importance of impulse response. Now we are going to learn what the frequency response is and how the impulse response is related to the frequency response of any system, and how we can determine the frequency response of any system with the help of its impulse response. Now this is very much amazing. We can determine the frequency response of any system with the help of its impulse response, but how, we will discuss it. For this, we have to consider a case represented in your slide under the heading of frequency response. Suppose you have a certain system, and what this system is, we don't know about it. We just assuming it as a black box. We don't know how this system process per certain input to produce accordingly output. So we creating this system as a black box at this stage, and we are interested to find out the actually what the system is. So to study the behavior of the system, which is a black box, in this case we have to do certain experiments, or we have to do certain mathematical operation on the system to actually find out its characteristic. So after obtaining outputs for different inputs, we can relate input and output and can predict the nature of the system, whether which kind of system it is and its behavior for certain kinds of input, because after applying certain types of input we know the corresponding outputs. So there are several methods for it. One method is to give different inputs to the system and observe the corresponding outputs and note the response of the system. By this I mean to say that, for example, at the input side I first set my input voltage as 1 volt as represented in this table also, and with the help of function generator I set the frequency of this input signal, this voltage signal, as 10 Hertz. And now I will see the output, which kind of output this system is producing. And after looking at output, I get to know that this system is producing 0.5 voltage waveform as an output. So this 0.5 waveform is actually the result of 1 volt input voltage at the frequency of 10 Hertz. So with the help of the available information, I can actually calculate the gain of the system, gain or attenuation. So gain is nothing but V out over V in. How much the gain this system is providing to my input. So it is calculated by using the relationship V out over V in. So after calculating the gain of the system for this particular frequency, gain comes to be 0.5. Now I will vary the frequency, keeping the input voltage magnitude constant as 1 volt. You can see that I kept the input voltage same as 1 volt and I am varying the frequency. So in the second step, I provide the input signal of 1 volt with the frequency of 100 Hz to the system. And suppose this system will give me the output voltage of 2 volts. So with the help of this available information, I can again calculate the gain of this system, which appears to be 2 volt, as 2 divided by 1 will be 2. So at 100 Hz, I came to know that gain of the system is 2. Now I will further increase the frequency to 1000 Hz, and at 1000 Hz I will again apply the same voltage signal, which is 1 volt, and I will observe the corresponding output, which is 3 in this case. So with the help of input and output voltage information, I will again calculate the gain, and gain appears to be 3. So the same procedure is repeated for other frequencies as well. You may notice that I am increasing the frequency gradually, keeping my input voltage same. By doing this, I am getting different values of output voltage, and by using the information of input and output voltage, I am actually calculating the gain. So this type of information is useful to actually plot the frequency response of this particular system. However, in the first stage or initial stage, I do not know what this system is and what it is designed to do so. But I am randomly applying different inputs and observing the corresponding outputs. And after compiling all the information of inputs and outputs in certain manner, I am actually going to predict or analyze the frequency response of this system is. So after completing my work, after completing this work or this table, I actually get to know that this system behaves like this at this input. So actually, if you notice the trend of the gain, which is increasing from 0.5 to 2 and 2 to 3 with the increasing frequency, and at certain frequency its maximum value occurs, which is at 1000 Hz, and after 1000 Hz I came to know that after increasing frequency further, the gain actually decreases. So I can plot the frequency response of this system with the help of this information, which is plotted in the next slide. So this is the frequency response. Actually, the random frequency response, or a rough estimate of the frequency response, if I plot the values obtained in the previous slide, you can see that frequency is on the x-axis and the output signal power, or you can rename this axis as the gain axis. So if you rename the gain axis, so you will get this type of curve, and this type of curve is actually showing that the gain is increasing for the initial values of frequency, and after certain limit the gain actually decreases. So we can say that this response or this frequency response is actually the response of a band pass filter, which means if I apply the frequencies which are very low, so this system will not provide significant gain to this frequency, or same will be true for very high frequency. If I apply very high frequencies to this system will provide insignificant gain to that frequencies. But if I apply frequencies which lie in this range, then this system will provide significant gain to this frequency. So this system is actually behaving like a band pass filter, which allows certain band of frequency to pass through this system and attenuates the other frequencies or remaining frequencies, which are the very low frequencies as well as very high frequencies. So this system is actually treating as or behaving as a band pass filter. Now, how sharp I want this response? This actually depends upon the designing of the system, that how actually this system is designed and how the coefficients of this system is set. Although this approach I have used to determine the characteristics or nature of the system of which is treated to be black box initially, is very much true, but you can see that this approach is not very much practical as well as not very efficient, because in real time we do not have much time to apply number of inputs to the system and observe the corresponding outputs and then deduce some conclusion from this magnetic data. So we need some efficient technique or some smart technique that will actually tell us the nature of this system without providing numerous input to that system and observing the corresponding outputs. So the second method is discussed, which is very much efficient, in the next slide.